अभी तो पार्टिसिपेंट्स आ रहे हैं।
2 मिनट में चालू कर देंगे।
हाँ 5 पे चालू कर।
हाँ, और अभी आपको तो सब इंट्रोड्यूस तो करने का जरूरत है।
उदय दास गुप्ता सर का लेक्चर क्या अब्रप्टली वो हो गया था क्या, अभी डिस्टर्ब हो गया था, मैं सुन रहा था।
अच्छा, हाँ, बाद में उन्होंने
तो
एट 3:30
फिर शाम में कंटिन्यू किया सर ने ना।
सामने है, अपना यूट्यूब चैनल पे अवेलेबल है।
जी जी देखा है मैंने।
हाँ,
तो मैं वही
3:30
सोच रहा था कि ये व्हाट हैपेंड मींस व्हाई अब्रप्टली वो।
नहीं, by he had a meeting by the ministry, सब
हाँ
मिनिस्ट्री का
वो
मीटिंग आ
मुझे
गया है।
मुझे लग रहा था कि कुछ तो अर्जेंट काम आ गया होगा।
हाँ, हाँ।
तो 26
अभी सर,
27 participants are there.
हाँ, yes, yes, yeah, I think there's no point in wasting the time.
We shall start now. Otherwise,
Initial, at least we can slowly start, na? You can go ahead, you can recap something.
yeah, yes. Okay. So I will
Yeah.
switch off my camera so that internet speed may does not cause any problem to anybody. So good evening, participants. Today we will briefly learn about the static diagram of static CMOS circuits, and subsequently we will do the layout using electric VLSI design system. So I will share my screen now and we'll begin. So Rathod sir, is my screen visible?
Yes, yes, yes.
In full screen mode? The slide in full screen mode?
Yeah, it is in full screen mode.
And am I audible?
Everything proper. Audio, video, slides, everything is proper, sir. Continue.
Thank you. So good evening, everybody. So let us very quickly learn a few things about layout of CMOS circuits, and then we will actually do the layout today. So there are different layers. So layout is actually geometric representation of circuit. Like we have a schematic representation of circuits where we use different symbols for circuit components like transistors, and among transistors also we have different schematic representation of N MOSFET and P MOSFET. Similarly, in layout, different components of circuit are represented by a combination of geometries, and those geometric figures, they actually represent different layers. For example, one layer would be the well. So we know that in CMOS process, we may have single well process or twin well process. Okay, so either we can start with P substrate, or we can start with, or we can have a twin tub process, which is also referred to as well. Well is the region on the piece of silicon where transistor will be manufactured. Similarly, we will have diffusion region. So diffusion region is also referred to as active region, which actually represents the source and drain of the transistor. Then we have polysilicon layer or polysilicon region. So that actually represents the gate of a transistor. Then we have a layer representing contacts. So it defines how the source, drain, gate, tap are contacted to higher metal layers. Then we have tap. So tap defines contact to substrate or well. So we know that the body of N MOSFET and P MOSFET transistors, they will be connected to appropriate potential. So for making that contact, that is referred to as tap. And then we have metal layer that defines interconnects between transistors or different components in our circuit. Now, design rules. There are certain design rules because we all know that the IC manufacturing process actually involves two things. The one thing is IC design, and another thing is IC manufacturing. So, and these two things, that design and manufacturing, they are taken up by two different set of people, and they have different premises also. Like the design houses, they will be located somewhere else, and the foundries where the ICs are manufactured, they will be located somewhere else. And two different set of peoples are involved in designing and manufacturing IC. So design rules are actually bridge or an agreement between the design engineers and the process engineers. Design engineers who are designing the IC, and process engineers who are actually putting the IC on the piece of silicon. So those two set of people must have some agreement between them, and this design rule actually is an agreement, and the process engineer asks the design engineer that if you design your IC following the design rules, I guarantee you that I can put your circuit on the piece of silicon. So design rules, you can also say, is a bridge between the design engineer and the process engineer. So here we see certain design rules, and these design rules actually put constraint on the minimum separation or minimum dimension between different geometries in the layout. So you can understand design rules like the set of rules that put constraint on the dimensions of the geometric figures that you use to represent circuit in the layout. For example, here this is an example of metal 1. So a design rule, and design rule also varies with technology. So design rule is not fixed for all the technologies, rather the PDK for different technologies, that will come with different set of design rules. So for a given design rule, for example, for a given technology, you can have a rule like you have a metal layer. So now the spacing between the two metal layers shall not be less than 4 lambda. Similarly, the thickness of this metal layer, or I shall say the width of this metal layer, shall not be less than 4 lambda. So this is actually a design rule for metal 1. And there are hundreds of design rules. So I have put only a few design rules here. So it is not that these are the only two design rules for metal 1. There are many other design rules for metal 1 that you can easily find in the PDK of a given technology, or if we are talking about the scalable CMOS design rules, so you can find those design rules in the SCMOS manual. Similarly, for metal 2, again we have a rule that puts a constraint on the separation between the two metal lines, that the separation between the two metal lines must not be less than 4 lambda. Similarly, the width of this metal line must not be less than 4 lambda. Similarly, for the diffusion region, so the separation between the two diffusion regions shall not be less than 4 lambda, and this is identical diffusion regions when I am talking about, to be specific. Similarly, for polysilicon, that the width of the polysilicon must not be less than 2 lambda, and the separation between the two polysilicon must not be less than 3 lambda. Similarly, we have design constraints or design rules on the metal to diffusion contact, that the metal contact must overlap this contact hole from all the sides by 1 lambda, and total it is 2 lambda by 2 lambda. Size of the this contact, size of this dark square, it is 2 lambda by 2 lambda. Similarly, here we have metal 1 to polysilicon contact. So again, this contact is 2 lambda by 2 lambda, and this metal 1 must surround this contact from all the sides by 1 lambda overlap. And similarly, between the two contacts, you shall have a separation of 3 lambda. So if we come to, this is a layout of an inverter, CMOS inverter. So where you see that this light blue region, this actually represents P plus active region for P MOSFET, and this is, there's a polysilicon gate that extends this diffusion region by 2 lambda. This is also referred to as poly gate overhang or gate overhang. Similarly, here also it will be there will be an extension, that is polysilicon gate will be extending beyond the active region by 2 lambda. So this dimension will also be 2 lambda. And here you can see that the separation between this N plus active and N well, it will be 6 lambda, and the separation between the edge of N well and P plus active shall be 6 lambda. So from here we can see, or we can say that the PMOS transistor and NMOS transistor must be put apart by 12 lambda actually. So this is a very small set of rules that I have put here. There are hundreds of design rules that, and nobody is expected to remember those design rules. Actually, these design rules are embedded into the layout tool, and whenever you violate those design rules, that layout tool will actually inform you. It will raise an alarm and inform you that you have violated a design rule. I saw a message from some participant. Isn't my voice clear? Am I audible?
Sir, everything is clear. Perfect, no issue.
Thank you. Then we have wiring tracks. So wiring track is the space required for wiring. For example, we have seen that the width of the wire or the metal lines are referred to as wires. So width of the wire is 4 lambda and the spacing must be 4 lambda. Therefore, 8 lambda also referred to as the metal pitch. 8 lambda is also referred to as the metal pitch. So you have a pitch actually is referred as the spacing between middle of this metal line to middle of this metal line, and that will also be 8 lambda. So that is how we refer pitch, gate pitch or metal pitch, like that. So this is 8 lambda. But you can also see that from this edge to this edge it is 4 lambda, and from this edge to this edge separation is 4 lambda. So metal pitch is actually 8 lambda. We will be using this information in calculating area of the layout. It's the approximate area of the layout, not the exact area. Exact area you can get only after doing the layout. But even before you have done the layout, you can have an approximate idea of how much area that circuit is going to consume on the piece of silicon. So if we talk about the transistor, so this actually represents the transistor. You have an underlying gray region from here to here that represents an active region. You have this polysilicon lying over it, and then you have a contact, source drain contacts, and you have a metal. So this shall have a dimension of 4 lambda. Then the polysilicon must be separated from this edge of the metal line by 1 lambda, and then 2 lambda, then again 1 lambda, then again 4 lambda. So from this metal to this metal, again you can see that it is 8 lambda, and from this center to this center it is again 8 lambda. So that is why you can say that the transistor also consumes one wiring track or it is 8 lambda actually, right? So let's go ahead. Then we have certain design rules on the well spacing, like the wells must surround the transistor by 6 lambda. That we have already seen that if this is the transistor, so and this is the well, this represents the well. So all the four sides of the transistor, that is this side, and this side, and this side, must be 6 lambda. This shall be 6 lambda, this 6 lambda, this 6 lambda, and this 6 lambda. And similarly for this, and therefore the two transistors, they will put apart by 12 lambda. And here it shows that if you have two transistors placed apart by 12 lambda, you actually have a wiring track, a space for running a wire. We actually look for spaces for running wire on layout so as to minimize the area of the layout. So that is what it highlights. We will see this situation in the layout this evening. Now here we can see a typical layout. So this layout is actually for 3-input NAND gate. This is a 3-input NAND gate layout. So this is actually NMOS transistors lying here, 3 NMOS transistors connected in series, and here we have 3 PMOS transistors connected in parallel. This represents VDD line, and this represents ground. So if we can count the wiring tracks, we can actually have an idea of the layout area. For example, one wiring track, second wiring track, third wiring track, fourth wiring track, and fifth wiring track. So we have 5 tracks in this dimension, and therefore 8 into 5, 40 lambda. We got this dimension 40 lambda. Similarly, one wiring track, second wiring track, third wiring track, and 4 wiring tracks. So we have got 4 wiring tracks in the vertical direction. So 8 into 4, 32. So we got 32 lambda. So we have an approximate idea of the dimension of this layout, that the vertical dimension of this layout is 40 lambda and lateral dimension of this layout is 32 lambda. And therefore we can calculate the approximate area of this layout by calculating the area of the rectangle by multiplying 40 lambda by 32 lambda. So this is how we actually estimate the area of the layout. Now we are going to quickly see the stick diagram that actually helps us in doing the layout, because directly starting the layout may put us in difficult situation. So if we have a stick diagram before us, doing layout will be easier, and we will have a process of doing layout with the help of a stick diagram. This evening we will see. So stick diagrams are means for capturing topography and layer information using simple diagram. We will be using only straight lines, okay? And this convey layer information through color code. So we will be using different colors to indicate the different layers of layout. And this stick diagram acts as an interface between circuit schematic. We actually want to go from circuit schematic to actual layout, but going from circuit schematic to actual layout may pose challenge when it's a complex circuit, and therefore doing stick diagram for a schematic to stick diagram and then from stick diagram to actual layout will actually be easier as compared to directly going from circuit schematic to actual layout. So a stick diagram shows all the components, contacts, and vias. Via, I hope you understand, via represents actually the contact between different metal layers, and contact represents the contact between metal and semiconductor. So a stick diagram, this shows relative placement of the components and goes one step closer to the actual layout, and it helps in planning the layout and routing. So we can say that a stick diagram is a cartoon of a layout, okay? And if we have before us that stick diagram, doing layout will be simpler. So let us quickly go through the different rules of a stick diagram. So here we see that different layers of the layout are being represented by different colored stick. For example, metal will be represented by this blue line, polysilicon will be represented by this red line, N plus diffusion will be represented by green line, and P plus diffusion will be represented by this brown line. If you want to do it in monochrome, so you can also use different line patterns for representing different layers. And I shall tell you at this point of time that these color codes are not the only color codes that you shall use for a stick diagram. different books or different manuals, they may use different color codes, and you can also use different color codes so long as you specify clearly which color you are using for which layer, or which line pattern you are using for which layer of the layout. Now, rule 1 of the stick diagram is that when two or more sticks of same type, cross each other or touch each other, that represents electrical contact. For example, this blue line, horizontal blue line, that represents metal, and this vertical blue line, that also represents metal, and metal one to be specific, for example. So if here they are touching each other, so when two sticks of same type, that is same color, they touch each other, it means that they are in electrical contact. Or if two sticks of same type, they cross each other, so it means that they are also in electrical contact. Here also it shows two polylines crossing each other, so it means that the two polylines are in electrical contact. Here the two metal lines, they touch each other, so it means that they are in electrical contact with each other. Rule 2 is when two or more sticks of different type cross or touch each other, there is no electrical contact. So when you have two different types or sticks of different types, so there is no electrical contact when they are simply touching or crossing. So here you can see that you have a metal line and you have a polysilicon line. They are touching each other, but you know that they represent different layers, and therefore there is no electrical contact between the two. Similarly, here you see P plus diffusion and a metal line crossing each other, but you know that they are in different layers and there will be no electrical contact between the two. However, sometimes we may have electrical contact between two different layers. For example, you have contact between polysilicon to metal, you have contact between source drain to metal. So you will be representing, for example, here you have polysilicon and you have metal. Now, your circuit connections may demand to establish an electrical contact between the two, and therefore you will have to exclusively indicate that this polysilicon and this metal is in electrical contact. So that exclusive representation of electrical contact between two metal layers can be represented by either a filled circle or a cross. So you can put a cross here or you can put a filled circle here, both that represents electrical contact between two different layers. Here also you can see that you have a polysilicon diffusion and then you have a metal line crossing each other, and if the circuit demands that they are in electrical contact, so you shall exclusively show that contact by placing a filled circle or a cross sign there in your stick diagram. Then third rule is when a polysilicon crosses diffusion, it represents a transistor. So we shall remember this, that how a transistor is represented in a stick diagram or in a layout. So you will have a active region. For example, here you have N plus active region, and you can see that a polysilicon line is crossing this active region. They are in different layers. Therefore, there is no, and you don't have any contact information here. So this diffusion region, active region, and this polysilicon, they are in different layers. And whenever you have a polysilicon overactive, it represents a transistor. In layout also, whenever you have a polysilicon overactive, it represents a transistor. So here you have a P diffusion, this line, horizontal line, that represents P type or P active region, and a polysilicon is crossing over it. So you have a poly overactive, so it represents a P MOSFET. Here it represents an N MOSFET. So you shall remember that poly overactive, that represents a transistor, unless until a contact is shown between the two. So here you can see that there is a contact shown between the two. So this does not represent a transistor. This does not represent a transistor because the active region is in electrical contact with the polysilicon here. The P plus active region is in electrical contact with the polysilicon layer here. So these two, they don't represent a transistor here. This does not represent a transistor here. Okay, this represents an N MOSFET. This represents a P MOSFET. Right. So rule 4 is in CMOS, a demarcation line is drawn to avoid touching of P diffusion and N diffusion. So to keep your stick diagram clear and clean, you can put a demarcation line and you shall try to put all the PMOS transistors above this line and all the NMOS transistors below this line, right? And later you will realize that this demarcation line is nothing but the boundary of the well. So this will actually be the boundary of the well. You will have N well for P MOSFET, you will have P well for N MOSFET, and this will be the boundary where the two wells actually touch each other. So let us quickly see that thing. We saw that the stick diagram actually is an interface between the circuit schematic and layout. So we have circuit schematic of inverter here and we have a layout of inverter here. This layout has been done using the electric tool that we will see this evening. So you can see for this inverter, so this P MOSFET, so you have a line representing P diffusion, and you for N MOSFET you have a line representing N diffusion. Then you have a polysilicon line crossing this P diffusion and N diffusion region. So that represents a P MOSFET. This represents an N MOSFET, and then you have this input V input applied here. Now you have a contact here. You can see that this represents a metal line, and this cross here represents that this metal line is connected to the drain of P MOSFET. This cross here represents that this metal line is connected to the drain of N MOSFET, and then the two drains are connected together, and this represents the V out terminal. Similarly, this polysilicon is in contact with this polysilicon that represents N MOSFET input to this inverter. And similarly, you have the source of P MOSFET connected to VDD. Actually, I need not to put this cross here. This is misplaced because this and this they are the same layer. So similarly, you have a contact between the source and the ground line of inverter. So this shows the stick diagram, and with the stick diagram, you can actually see that this P MOSFET here. So this region corresponds to the P MOSFET here. So this is the P MOSFET here. Similarly, this is the N MOSFET here. So here you have placed N MOSFET here. Okay, and this is metal line. This metal line corresponds to this metal line. This polysilicon corresponds to this polysilicon, like this, and this VDD line corresponds to this VDD line. This ground line corresponds to this ground line. So this is how we can go from a schematic to a stick diagram, from a stick diagram to layout. Now, how can we represent a stick diagram? So that previous stick diagram was simple because we had only one P MOSFET and we had only one N MOSFET. So that was simple. But actual circuits that we may deal with may not be that simple. So there may be more than one N MOSFET and more than one P MOSFET connected in series or in different fashion. So suppose you have four P MOSFETs connected in parallel. So when you have four P MOSFETs connected in parallel, how can we draw the stick diagram for this? So first of all, while doing the stick diagram, we shall actually draw the Euler's path for this network. So you have this parallel network of P MOSFETs. So Euler's path tells us what? That you shall traverse all the branches without traversing any branch more than once. So how can we do that? So we can start here. We can start here and we can go like this. We can go like this. So this is one possibility. This is one Euler's path, and this Euler's path. So we can say first we are going from, so this you can say this is source of this P MOSFET. This is drain of this P MOSFET. Similarly, this is source of this P MOSFET. This is drain of this P MOSFET. Similarly, this is source of this P MOSFET. This is drain of this P MOSFET. This is source of this P MOSFET, and this is drain of this P MOSFET. Okay, and to be specific, so I can say that this is S1 and this is D1, this is S2, this is D2, this is S3, this is D3, and this is S4, this is D4. Okay, so you can have a Euler's path that is going from source 1 to drain 1, and then drain 1 and drain 2, they will be merged actually. So that is what is you are seeing here, that you are having a P diffusion region and then you are putting sticks. So you are going, so your Euler's path, you are going from left to right, you are going from here to here. Okay, so this represents actually S1, this represents D1, this represents D2, this represents S2, this represents S3, This represents D3. This represents D4. And this represents S4. Okay. So I could have started here and gone like this also. So this second case is for that. Let us leave that. So now you can see that when you are going from left to right, so first you have the source of A1, then the drain of A1 and drain of A2. That can actually be merged, because you know that they are symmetric in nature. So drain of A1 transistor and drain of A2 can be merged. Similarly, source of A2 transistor and source of A3 can be merged. Similarly, drain of A3 and drain of A4 can be merged, and source of A4 will be here. Now you can see that all the source, they have to be connected to VDD. So you will take a connection from here, a connection from here, a connection from here, a connection from here, and that will be connected to VDD. And then the drain of all the transistors are connected together. So you have the drain of A1 and A2, then drain of A3 and A4. So you will join them together. So now you have actually, so this stick diagram represents this connection. This stick diagram also represents the same parallel connection of 4 PMOS transistors, but for that the Euler's path is actually different. So for this stick diagram, I have taken a Euler's path like this. I have started from here and I have gone like this. So you can go in any way. So I have started here and I have gone like this. So this actually represents this stick diagram. Fine. Similarly, let's see the stick diagram for series connected transistors. So for series connected transistors, you can see that you can start from here and you can go here. So how do you go? You go from source of A1 to drain of A1. Now drain of A1 and source of A2, they are merged. So you are going from source of, you are going from drain of A1, D1 to S1, and similarly D2, S2, D3, S3, D4, S4. So similarly, you are going from here D1 to S1, and this is also D2 to S2, and like that. And since source and drain of A1 and A2, they are merged, so that same active region can be used as source for A1 and drain for A2. So this is how you can draw the stick diagram for series connected transistors. Now, if we join the 4 parallel transistors and 4 parallel P MOSFET and 4 series N MOSFET, so you get a 4 input NAND gate actually. So this 4 input NAND gate, so you can put the stick diagram of 4 parallel P MOSFETs and 4 series N MOSFETs together, and you can get the stick diagram of the 4 input NAND gate. Now at this point of time, we will have that case in next example. Now I have taken a little complex example, and we will be doing the layout of this circuit actually. This evening, I will be demonstrating the layout with the example of this circuit. So when we have to draw the stick diagram of this circuit, first of all, we shall find a Euler's path. So there could be multiple Euler's path for pull-up network and multiple Euler's path for pull-down network. There could be multiple Euler's path, no issue. Okay. For example, one Euler's path that you can start from here, you can go here, you can go here, and you can go end up here. Another Euler path for this network could be that you start, for example, how can we do that? Yes, we can start here, we can go here, we can go here, and we can go here. This is another Euler path for pull-up network. Similarly, you can have multiple Euler's path for pull-up network. Okay. So, and this red one. So for red one, the Euler path is we started with transistor B. So you will have B. Then we went to D. So you have D. Then we went to transistor C. So you have C. And then we went to transistor A. So you have A. So this is the Euler's path for the red path. Similarly, if I write the Euler's path for this, so this is we went to C, then from C to A, then we went to B, and then we went to D. Similarly, you can have many other Euler's path. Fine. Similarly, let us draw the Euler's path for pull-down network. So for pull-down network, let me change the color of the So for pull down network, one Euler path could be that you start from here, you go here, you go here, and you end up here. Okay, and this Euler path, you can say that you go from D, you go from C, you go to A, and from A to you go to B. This is one Euler path. Okay. Similarly, another Euler path for this pull down network would be you start from C and you go to A, you go to B, and from B you go to D. Okay. So this Euler path, you can say that this is C, then you are going to A, then you are going to B, then you are going to D. Now you have multiple Euler's path for pull-up network and pull-down network. Which Euler path we shall choose for doing the stick diagram? So now here is the condition that you shall have same Euler path, means order of these transistors shall be same for both the pull-up network and pull-down networks. For example, you can not take this Euler path for pull-up network and this Euler path for pull-down network because the order of the transistors are not same. Similarly, you cannot take this Euler path for pull-down network and this Euler path for pull-up network because order of the transistors are not same. And there is a reason for. So if we see, we can see that this Euler path for pull-up network and this Euler path for pull-down network, they have same order of transistors. Therefore, we shall choose this Euler path. Actually, what happens? The order of transistors here are related to the order of these polysilicon gates that you put. So if you have same order of the transistors for pull up network and pull down network, that will actually enable you to join the two polysilicon by a straight line. So you can see, and that is actually a preferred or desired situation in doing the layout. So you could directly connect the gate of this P MOSFET and this N MOSFET by a straight polysilicon line. So if you choose Euler path for the pull up and pull down network such that the order of the transistors are same in both the paths, you will actually satisfy this requirement and you will have these straight poly lines uh, connected to the P MOSFET and N MOSFET. So that is, and this is the stick diagram for this circuit, right? Let's go ahead. So now, before we go on doing, so a stick diagram actually does not need that we size the transistor first. Means you need not to have the transistor sizes available for doing the stick diagram. We don't need that because stick diagram does not show exact size of the transistors. They only show the placement of the components and the interconnection between those components. Actual size of the transistors, they are not, that information is not there in the stick diagram. However, when we need to do the layout, so in the layout, we must have the exact size of the transistors. Okay. So before we go and start doing the layout of the circuit, first of all, let us size the transistor. So let us say that this is the reference inverter. So, and you have different path, different pull-up path from the output node to VDD and different pull-down path from the output node to ground. So if we talk about the pull-up path, so you have one pull-up path going through B and A, another pull-up path going from B and C, and another pull-up path going from D to VDD. Okay. So now in this pull-up path, you have two transistors in series. Therefore, the size of the transistor will be double that of the transistor in P MOSFET inverter. So here it is 10. So we will make it 20. In this path also, you have two transistors in series. So we will double the width of these transistors as compared to the width of this P MOSFET inverter. Here you have, in this path, you have only one transistor connected between the output node and VDD. Therefore, the size of this transistor will remain same as the size of this inverter because here also you have only one transistor sitting between the output node and VDD. Right? So you have 10. Let us come to the pull down path. So you have pull down path, one pull down path to this, to these transistors, another pull down path through this transistor. So in this path, you have three transistors in series. Therefore, you must make these three NMOS transistors three times as wide as the NMOS in this inverter. So in this inverter, this NMOS is 5 units wide. So we have made this 15, 15, 15. And in this path, you have two transistors in series. So I have made this we have already sized. I have made it 10. You could have done it with a little smaller width also because we have made it 15. So you could have done it with 7 or 7.5 also. But let it be can, no issue. So this is what we do, how we do the transistor sizing for matching the pull up and pull down strength of the circuit, right? And then using this stick diagram, this layout has been done. So now I am going to do this layout. I did this layout this morning. So I will do it again before you so that you can see how we are doing the layout. So this is it. This was what I wanted to discuss in the context of a stick diagram. So let's go and do the layout for this circuit. So this circuit, we will be doing layout for this circuit. Okay. So now I'll go and I will invoke electric. Fine. So Rathore sir, I hope my screen is visible and electric that I invoke is seen, can be seen.
Yes, sir. It's coming, sir.
Okay, thank you. So now I will open. So now you see I have created this schematic this morning. I created because the DRC LVS that we are going to see. So for that we must have a schematic also. So this schematic I did this morning, and this schematic is same circuit that I just showed you in the slide. It's that same
सर
circuit
अभी तक आया
schematic.
नहीं है नौशाद सर अभी तक आया नहीं है आ रहा है इट हैज नॉट कम जस्ट
Can you see the schematic?
नो
Schematic is
एक
not visible.
नो एक काम करो आप स्क्रीन शेयर यू अगेन डू द स्क्रीन शेयर
Okay, let me do it again. Is it visible now?
नो हाँ वेट या इट इज कम
Is it visible?
या इट इज
Okay, thank you. And is it okay to have white background clarity?
हाँ यस दैट्स बेटर
Okay, thank you. So I have already done the schematic because we have already learned how to do the schematic in electric. So I will not be demonstrating this schematic again. It will unnecessarily consume time. So what I did actually, I went to this library and I added a cell, new cell, and then I named the cell as a example. I have named it example, and then I chose a schematic view and I clicked OK, and then I created this schematic. Now we are going to see how we can do the layout view of this cell. Okay, so I will again select this library. I will go to cell, new cell, and in this new cell I must put the exactly same name. The name of the schematic view is example, so I will put the example as the name, and now I will select the view as layout because I want to do the layout of this circuit. Therefore I will select the view as layout. Fine. Now I will click OK. So now you see that a new window has popped up. Okay, let me turn on the grid. So grid I have turned on by going to window and clicking on the toggle grid. Now if you can see that a plus sign has appeared actually. So now this example, this cell is having two views. One is the schematic view that I have already done, and another is the layout view that I need to do. And you can see that when you do a schematic view, you see a different components here that we have already seen. Now, when you select layout view, you see a components that you need for layout. So that you can see here. Now you have different component list under this component when you do the layout view. So we will be doing the layout now. Okay. So let us start with the layout. So in this layout, we need 4 P MOSFET and 4 N MOSFET. So let us first complete the P MOSFET. So here you can see you have different layers, and whatever layer you select actually, that information will be shown over here. You can see over here what is that layer actually. For example, if I select here, so if I bring my mouse here, so you can see in this region, you shall notice here, when I bring my mouse at different layers, so this shows metal 1, this shows polysilicon 2, this shows an active region, this shows P active to metal contact, this shows N well, this shows N MOSFET, this shows P MOSFET. So you have different layers, and as you move your mouse over different layers, that information will actually be shown here. Okay, so let us begin with the layout. So we need 4 PMOS transistors. So I will again, how can we bring these transistors? So I will bring my mouse here on the PMOS. I will left click and release the mouse, and I will bring it here. This thing got attached to my mouse. I brought it here. I will again left click. So now this PMOSFET got placed at this place. Okay. Similarly, I need 4 PMOSFET. So I will repeat this 4 times. So I have placed all the 4 PMOSFETs here. Right. Now I need to rotate these P MOSFETs because right now the polysilicon, the pink region that you see, that represents polysilicon, and the green region that you see represents the active region. But I want to run my polysilicon in the vertical direction. So what I will do, I will go here and double click. So when I double click, I can fix the width of the transistor, and I can also rotate it. So I first of all, let us fix the width of the transistor. So the size of the transistor, let's say this is a transistor corresponding to transistor C, and the size of the transistor is 20 lambda, and I want to rotate it by 90 degree. So I will do it. So I have got a transistor that is 20 lambda wide. So because in the stick diagram, the first transistor is transistor C, and the width of the transistor C is 20 lambda. So I have got this 20 lambda. Fine. Subsequently, I can change the width of next transistor. In the stick diagram is A, and the size of the transistor A is also 20 lambda. So I will make it 20 lambda, and I will also rotate it by 90 degree. So I have got this transistor here. Similarly, the next transistor in the stick diagram is transistor B. I'm talking about P MOSFET only. So transistor B, and transistor B, size of transistor B is also 20 lambda. So I will make it 20, and I will also rotate it by 90 degree. So this is it. Okay. And then we have another transistor. So this is transistor D actually, and the width of the transistor D is only 10 lambda. So I will put 10 lambda, but I will rotate it by 90 degree also. So I have got this. Okay. Now I have to place contacts. So because right now you see only active region and you see this polysilicon region, and this actually represents the well. This represents the outer shaded region represents the well, and inner light yellow actually represents oxide layer, and then green region represents active region. So in this tool, actually the active region of both PMOS and NMOS, that is represented by green color, and the distinction is made by the pattern of the shade. Fine. Now I have to make a contact, source drain contact. So I can see this N contact and P contact. So we know that the active region of P MOSFET is P type, and when you bring it here, you can see that the information is populated at the bottom that it is metal 1 to P active. So I want to put a metal 1 to P active contact. So I will put it here. And first of all, I can do what? I can bring it my mouse here, and when I left click, it gets selected. Then I will release the mouse button and bring my mouse here. And when I right click here, this gets connected. So now it is in contact. Now this is only one contact, but this is 20 lambda wide transistor. So it is possible to put more than one contact. So I have decided to put 2 contacts actually. So I will do what? I will exercise remain same Y size. I will make 10. So now you can see that I have got 2 contacts. Now what I can do actually, I can bring my mouse here, left click here. So this contact gets selected, and then I can adjust it, and then I can, with the help of the arrow key, I can bring it closer, and I can bring it as closer as this thing. I hope this is correct. So, okay. So now I can, at this point of time, I shall run actually DRC. So when I run DRC, you see that here it will be reported that 0 errors and 0 warnings. So it is always good that when we start doing layout, we run DRC as frequently as we can, because if we avoid running DRC more often, so what happens, the errors they accumulate, and when you have done many tasks in the layout and then you run DRC and then you see 10-20 errors, so that actually becomes very difficult to correct those errors. So that is why I will suggest you, and I also practice that same thing, that we do the layouts, we run the DRC as frequently as possible. So initially at every step, now I am selecting this whole thing and I will actually move it a little apart so that I can put a contact here also. So I will again select a contact, so P active contact. I will bring this contact here and then I can also make it 10 lambda. Okay. So, and then I can make the electrical contact first. So left click and right click here. So this makes the electrical contact between the two. You can see that when I click this contact, it shows this dotted red line. It means that this contact is this is in electrical contact with this transistor. So now I again select it and with the help of arrow key, I bring it closer. So I can bring it as close as this thing and I make it more close. So this way, and then again I run the DRC. Check DRC. So again I see zero errors and zero warnings. So far, so good. Now, in adjacent to this transistor, we have another transistor which is transistor A. So I shall bring transistor A a little closer and then I shall uh, make an electrical contact between the two. So I will select, bring my mouse here, left click here, and then I bring my mouse here and I right click here. So this establishes electrical contact between the two. Now I will bring this transistor closer so as to the area, right, and let me run the DRC if everything is fine. I can also run DRC by clicking F5 shortcut. Now you can see that there's error. It shows error. Layout, yeah, fine. It shows error. So I will, when I click OK, you see a message here. To see the error, you can, I will press Shift and greater than or smaller than. Yeah, I shall Shift and, okay, just a minute. So it shows me F5 DRC errors. So now we have, or open the error view. So error view, type this or this step through errors. Okay. So why it is not showing? It should have two errors. Okay, I shall go to this error here. You can see, and we can see the error here. Yeah. Now clicking on this, it is showing me error, right? The error is highlighted. Now you can see the error, highlighted error, and here also. So what is the error? You can see that the error is that PMOS transistor and these two transistors. So this error is actually because the two active regions, they are not separated by the desired space. Fine. And this is Moses rule number 2.2. So if I show you the Moses rule, okay, let me show you Moses rule first so that we can relate it. So we can see the Moses rule first. I will go to layout and then I will open the Moses rule. So is my screen visible? Moses rule. Do you see the Moses rule? Yeah, it is visible.
हाँ सर दिख रहा है.
So if I go 2.2, so you can see the rule 2.2 here. So you can see that rule 1.1, 1.2, this is related to the well. Similarly, 2.2. So now you can see that scalable CMOS layout rules that we are using. So this is for active region. So rule 2.2, you can see that it is about minimum spacing. That the minimum spacing between the two active regions shall be 3 lambda. And here it is indicating that it is only 1.5 lambda. Okay, but we know that these two active regions, we are actually having shared source drain for the two transistors. So these two active regions can actually be merged, right? So what we can do, we can go to component, and we can go to pure, and in this pure, we can select this P active node. So this actually puts a P active region here, and then we can make this 20 lambda. So this will actually cover this. So now we do not have the separation. So let me again run the DRC and see if that error, okay, that has made some more errors. That actually happens when you do the layout. Okay, this was not electrical contact. Okay, let me like this. 20 lambda if I do, and either end I select fine. So now I put it here like this. So let me again run the DRC and see. Right, now you can see that I have removed that error. So actually I have merged the two active regions. So now it is not violating any design rule. Fine. So we have placed the two transistors, transistor C and transistor A. Now it's time for transistor. So, and I shall also place a contact here on this side. So I will again bring a P active contact here. I will bring it here and let me change the size to 10 lambda. Okay. And then I will align it with the help by selecting it and with the help of that arrow key, and then I shall have an electrical contact between the two. So I have done that, and then I will bring it as close as possible without violating the design rule. So let me check the design rule. So I have not violated the design rule. So I have placed this contact here. Now adjacent to this transistor, I have transistor B. So this is transistor B. Okay. So I shall have an electrical contact between this and this. So I have got that. Now I will bring it as close as possible, align it with the help of arrow key. So as close as possible so that the design rule is not violated. DRC. Now it is full of DRC, and we know what this DRC is. This DRC is about this spacing. So how can we solve that? We can right left click here, we can right click here, the two activities got connected. Then when you bring your mouse here, double click on it and adjust the width of this. So 20 I will adjust, and okay, oh no, I did it. I shall select one end only. So what it happened actually when I made it 20, both ends. So it is extended by 20 lambda in both ends. So I will select either end and then I will click OK. So now you can see that it is going like that, and with arrow I have done this. So now let me again run DRC. Fine, no DRC error. I have removed that error. Good. I have placed transistor C, A, and B. Now the last transistor that I am left with. So let me bring that transistor close to this. So before that, okay, before that I shall place a contact here also. For this, so I will again bring a contact. I will place that contact here. Double click and then change the uh, y direction and dimension, and then I will move it with the help of arrow key. Okay, and then make the electrical contact between the two. So left click, right click, done. So I will bring it closer, as close as possible without violating the design rule. So I have brought it, so I can see that no errors. Fine. Now I bring this transistor closer, and this transistor has to be in electrical contact with the other transistor. But why I am putting it like this will be clear in a moment. But for now, you allow me to do this. Okay. So okay, I will make this right left click and right click, and then I will make it 10. So and neither end, okay. So now I have this, so this transistor I shall bring it. Now I will bring this transistor close as allowed by the design rule. So let me run design rule. So can I bring more close? Okay, can I make it closer? Fine. So I can bring it this much close, I think. That's okay. Fine. So I have placed transistor C, transistor A, B, and D. And now let us make the well and VDD contact. So I need to put a contact here also. So I will take P active here. I will bring it here. Then I will do a electrical contact between the two, and I will change the dimension by double clicking on that. So I change the dimension, then I will bring it closer, align it, and how close I can bring. So I think I have violated. Okay, no, I have not violated. So this is how we can place all the four P MOSFETs. Why I have made these contacts not here, this contact not here, and this contact not here will be clear in a moment. But it would have really consumed time for me that I initially put the contact all over the active region and then again edit it. So it will be clear by putting, because from the stick diagram, I know that this region and this region need to be connected. So if I run a metal like this, so it will actually increase the area. Now putting these two contacts here and putting this contact here actually allows me to run a metal from here directly, because that metal is in a different layer and the polysilicon is in a lower layer. So you can run a metal directly from here to here, okay, and you can make a contact. Fine. So now let me bring the well contact. So I can put a well. So which well I shall have a contact between N well and metal one, because P MOSFET that is formed in N well. So I will bring this N well here, and now I need to extend this N well, right. So I will extend this N well like make this by. So I can see that 1, 2, 3, 4, 5. So for lambda, I shall make 40 lambda. I make 6 lambda. Okay. Okay. That's not. I shall make x 40 because I want to run that. Okay. So that's it. That is well. Actually, I can make it a little longer, but okay, leave it. It's not. Now I shall bring this as close as possible. Okay. So from let me see. Let me check the design rule. Have I violated? Yes, I have violated, and all those design rules I have violated actually. So now it's okay. So okay, I am keeping it at this separation. You can actually optimize this separation by iteration or by having this design rule before you. This design rule actually, this copy of design rule before you will help you to do that. So I will okay go ahead with this separation. Okay, and then you can see that this well contact is actually having a metal one running over it. Okay, so now I can do what? I can take this left click on this metal one and right click on it. So you can see that this source of these two transistors they connect have got connected, and this transistor, source of this transistor, and this shall also be connected. So I have connected the source of these two transistors. So this metal contact is done. Then what is left? Okay, I shall also assign models, SPICE models to these transistors, right? Because we have to run simulation. We have to run simulation, and to make this look better, what I can do, I can make it 40 48 lambda. Let me see. Yeah, yeah, now it looks better. Let me run the DRC again. Fine. So that's it. Okay. Now I can actually assign the SPICE model. So I will bring my mouse here, select this transistor. I will go to tools, and then I will do a SPICE, set a SPICE model. Now you can see that now here what happens, that it is really difficult to select that. I want to edit that SPICE model that has been placed here, but I'm not able to select that. So how can we do that? First of all, let us actually maximize it by going to window. Now actually I want to change this name, so but I am not able to select it, you can see. So how you can do that, you can actually press control button and then click, and one by one every layer will be selected. So now you can see that that spice model got selected. Now I will double click and now it becomes editable. So this is PMOS, fine. I was assigned. Now I will select this transistor, go to tool, spice, and then set a spice model. So again, I'm trying to select it. I'm not able to select it. So I will press control button and then I can select it. So PMOS, fine. Then I select this transistor, go to tool, spice, set a spice model, control button, and then select it. So now PMOS. Similarly, for this transistor, go to tool, spice, set a spice model, press control button, bring your mouse here, double click, PMOS. So I have set the spice model for all the transistors. They are all PMOS transistors, fine. And if we want to do that, okay, so this is it. Now I shall minimize it and create a space for placing. So Control Z, with Control Z I can do actually that. So sorry, control 0 I can do that. Control 0 I can minimize it, fine. Now similarly I will do the connections of the NMOS transistors. Okay, so now I will do the connections for NMOS transistors. So let us bring NMOS transistors, 4 instances of NMOSFET. So I bring one instance of NMOSFET, second instance of NMOSFET, third instance of NMOSFET, and fourth instance of NMOSFET. And again, we need to rotate it and size these NMOSFETs. So from the transistor sizes that we have done, and from the order in which we need to place. So first is the transistor C, and transistor C, width of the transistor C is 15 lambda. So let me edit it. So make the width 15 lambda and rotate it by 90 degree. So I can rotate it by 90 degree. Okay. So that's it. Uh, then I shall make contacts. So I can bring a contact. Now this time I need a N active contact between this N active region and this region, and I will make, so I can make it 15 lambda to have contacts all over the source drain region. Okay, and let me run the DRC. So no error, so far so good. So now I need to place another transistor, which is transistor A, and the width of the transistor A is also 15 lambda. So I'm using this as transistor A. So this is transistor A. I will make it 50 lambda and rotate it by 90 degree. 90 degree. Okay. So I will bring this transistor closer, then make electrical contacts. Okay. Now I have to bring this transistor closer, but how closer? Because we know that this poly has to be connected to this, and this poly has to be connected to this. So the poly spacing here between these two transistors, or the poly pitch for these two transistors, shall be same as the poly pitch here. So can I have an idea of the poly pitch? So what can I do? I can actually bring these two entities closer, and then I can zoom it so that I can see the two together. And then how can I? what I can do actually, I can see that this transistor can be, sorry, okay, I will bring this transistor closer to this transistor. So I can actually select actually, and I can actually go and match actually like this also, no issue. I can do that, and then I can bring it apart. So select. So I have matched the pitch of the two polysilicon. Now this active region, this will actually cause an error because this shell cannot be closed, this closed. So I will go here, I will make it 15 lambda and neither ends. Okay, so fine. So this is how we can place. Okay, we can also run a DRC to see. Okay, DRC reports that there is no error, so it's fine. Now let us bring other transistors here. So I shall bring other transistors also here. Okay. So now I have brought another transistor. Now if we see the layout, we need to put up. So this transistor is actually transistor B, and transistor B is 10 lambda wide only. So I will make it 10 lambda and rotate by 90 degree. So this is fine. And we will bring this, we need a contact also between these two transistors. From the stick diagram, you can see that. So we will bring this inactive contact here, and I will actually left click, right click. Similarly, so I will actually have only one contact between these two transistors. Okay, yeah. So let me see. Yeah, fine. And similarly, I will bring this closer and I will align this edge of, because we have different width of transistors. So for P-MOSFET, I have aligned these edge. Okay, here you have this space. Similarly, for N-MOSFET, I will align the bottom edge of the transistors. Okay, so right click and then I bring it closer. So how close I can actually bring it? Yeah, I think it is fine. Okay, fine. So now I need to place because that will actually result in error. You can see that you have an error. So that error is because of this. Okay. So that you can always go to error notch and you can always see the error, that you can see this highlighted. Error gets highlighted. Okay. So we will left click, we will right click. Okay. And we will make this as wide as 10 lambda, 10 lambda, either ends. Okay, so this got fine. I hope now the error is removed. Yes, error is removed. So this is fine. Now we need to put the last transistor, that is transistor D. And from the sizing, we have seen the width of the transistor is 15 lambda or 10, yeah, 15 lambda. Width of the transistor D is 15 lambda. So I will make it 15 lambda and rotate it by 90 degree. So that's it. And I need to put contacts also. So I will put contacts first. Let me bring contacts from this component tab. So N active contact, I will bring it here. I will make this contact as wide as say, I could have kept this okay. Mm, yeah, I can keep it single also, leave it, no issue. So left click, right click, similarly left click, right click. So I will actually take this contact as close as allowed by the, and then I will So I can select multiple regions like this transistor, left click and then pressing shift and contact. So all that got selected, and then with the arrow key I can actually move this. So here now I can bring it this much closer, I think, or a little part. You, am I able? I need to bring it a little closer. Fine. So again, you have a separation. This will cause an error. So left click, right click. So and then you select this thing and adjust the width of this thing by 10 lambda. And I shall tell you that doing layout in Cadence is a little easier than what we are doing right now. But then that's the trade-off between having a free tool and having a shelling out 14, 15 lakhs for the tool. That's actually the trade-off. Okay. Now I need to put a contact here also. So I will bring an active contact and adjust this contact. So suppose I want to put the contact over all of this active region. So I will adjust the size to 15 lambda. Fine. Then I will establish the electrical contact. Left click, right click. Then I will adjust it. Yeah. Bring closer. Let me see. I have brought it. Let me check the DRC. Fine. So now I have put the transistors. Now you can see the active region width different. So these active regions actually represent the width of the transistors. Now what is left? First of all, let us assign a SPICE model to these transistors. So this is N MOSFET. So I will select it and I will go to Tools, SPICE, set a SPICE model, and then again I am not able to select. So I will actually zoom it. Okay, I will zoom this region by pressing Control and 7, or I can do it from you also. Then I will select. I'm not able to. Yeah, selected NMOS. Fine. Then I will select it. Zoom. Set a SPICE model. So Control. Then NMOS. Then I go to this transistor. Go to Tool. Set a SPICE model. Yeah. Select it. Uh, NMOS. Similarly, I go to this and do the SPICE model, select the SPICE model, then Control, then NMOS. So I have set the SPICE model for these transistors. Then I can zoom it a little. Now I shall do the well contact for MOSFET, and then I shall do the ground line. So I will go here, and these grids, these small grids actually represent 1 lambda, and these dark grids, they are 10 lambda apart. So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this dark dots, they actually are 10 lambda apart, 10 lambda apart, and these lighter dots, they are 1 lambda apart. Anyway, so let us place the well contact. So N MOSFET is formed in P well. So we will bring this P well here, and this is P well. So let me adjust the width of this P well. So that shall be, I think, 45. I can make it a little wider. So 50 and make it 6. Yeah. 50. Okay, let it be. So now you can bring it as close as this oxide merges to a hierarchy. So you can see that no design rule error. Now I have to connect. So this has to be connected to the here. Fine. So I have connected this. Okay. So similarly, I can actually bring this little blue. If I turn it black, so let me toggle. So that is actually black background. Yeah. So actually, this yellow shade and this yellow shade can be merged. Means you can bring it as close as that. So now it is close. Now I can fill window. So now you see the PMOS transistors, the well contact and the PV line, the NMOS transistor and the well contact and the source line. Now we have to connect the polysilicon gates of the transistors and we have to bring out contact. So now first of all, you see the stick diagram that the drain of this PMOSFET and drain of this PMOSFET that is connected together. So I can left click here and I can right click here. Okay, this actually goes that. Okay, I will left click, right click, right click, right click. So and now I can bring it over it to save upon area. So if I run DRC now, let me see two errors I have. So what are those two errors? I can go to Explorer. I can go to errors. Errors. I can click. Okay, I have brought it closer. I think the metal node be active. So you can see the error here that node 6 to node metal 1. So it has violated the design rule. Okay, and what is that? So what is this design rule error? You can see less than 1 lambda. So okay, shall I bring it apart and run the DRC again? So it's again showing error. Let me see what error I made. So node metal 1 P active contact uh, less than 6 to node metal 1. Moses rule 1.3. So let me go to Moses rule 1.3. Let me see. Moses rule 1.3 tells us that minimum spacing between well at same potential shall be 6 lambda. Minimum spacing between well at same potential shall be 6 lambda. So okay, it is. I think okay, it is. It is. I think these two wells shall actually be merged. This well spacing is actually causing this error. So okay, let me maximize it. What I guess that you see, uh, you have this corner. You have this corner and this corner. So 1, 2, 3, 4, 5. This is not 6 lambda apart. You can see this well is not 6 lambda apart. Okay, so this is actually causing this error. So okay, what I will do actually, I will bring it like this, and then this is only 5 lambda apart. 1, 2, 3, 4, 5. 5 lambda apart. So how can I do that? So I will go to component, then floor, and this is n well actually. So n well. So I will select n well from here, n well node, yeah, n well, and then I can actually put that n well. So did I select that n well? Yeah, now it is selected n well. So what I can do, I can actually put n well like this. So that's it, and let me run it again. Let me run the DRC again. So run DRC. Oh, thank you. There's no error now. So that well error was there. Uh, so that's it. Now we are going to join the gates of the transistors. Okay, let us first complete some more connections. I think it is left. We have some more connections left. I need to connect these also. If I see the stick diagram, I need to connect these two transistors also. So I cannot run metal line over here. I will have to run metal line like this. So I will run that metal line, left click, right click, and then left click. So this is how I can connect, and then I can adjust this by selecting and with the arrow key. So let me run the DRC again. No error. So I have made the connection of the drain of these two transistors. The source of this transistors is these two transistors are grounded, and this is actually the merge. These two transistors are connected in series, so you don't have any contact there. And this is actually the output node, and this is actually the output node. So that we will connect later. Let us first do what? We need to actually create a space between the two transistors. So now I will do what? I will select all this and I will bring it down, and I will actually create a space for running the connections for these polysilicon layers. So how can I do that? Let me maximize it. Maximize it. So now I need to do a contact between polysilicon and polysilicon lines will be brought out, right? So okay, so I will select this. This is actually metal one and polysilicon. So I will bring this metal one and polysilicon. So I will bring it here. I will bring it here, and let me see how close I can actually. Okay, let me first extend this polysilicon to this. Okay, and then left click and right click. Oh no, not this. Left click and right click. So now you have this. So now you can see I can bring this polysilicon out to this much closer. Let me run the DRC. Fine, no error. And then actually you will have a metal line running from here to here. So this is polysilicon. So not the polysilicon metal. Okay, good. How can I do that? Okay, I shall. Yeah. Okay, I will do that. I think I need to place a metal pin. Metal pin. I need to place a metal pin here, and then I need to run a metal line. So this is how I can do that. Let me run the DRC again. So no error. Fine. Now I will extend this polysilicon a little lower, and then I will use a contact between metal and polysilicon. Select this, left click, right click, and then I will have a I will have to bring it closer. So now you see how can I run this metal. So this, if I place it here and I right click here. So let me run it the DRC. DRC. So now it is full of error. So what is this error? Actually, let me see. So I can see this error. The error is polysilicon one less than metal. Rule number 3.2 is violated. So this rule number 3.2. So what is that? These two edges they are actually close. So what I can do actually, I can bring this like this. Here also I can do it like this. This is allowed in design rule. Now I shall again run the DRC. So now there is no error, you can see. No error. So initially you will have to refer to the that Moses rule file. Now I bring again a contact. So I have this then left click, right click, what they get connected. Then I can bring it this much close. Then I will select a metal one pin. I will place a metal one pin, one, two, three. Okay, one, two, three, like this. And then right click. So I have this. So let me see. No error, fine. Then I have to bring this. Okay, let me do a little. This polysilicon down like this. And then I will again, oh, stay a little more. Then I will again take this metal one and contact. So I will put it here, left click, right click, control Z, left click, right click, so it got connected, and then I will put it here like this. Then this metal pin I will choose and I will put it here, left click, right click. So okay, control Z. I think this has become a, so I can always do a control Z. Awesome. I put a fine. So let me run our DRC now. So it is error. So what is that error? Let me see. So here I have made some error. Oh, yes. So initially it becomes actually iterative process. So this thing I shall better delete. Uh, again, left click, right click, and then I shall bring it here, and then I shall put a metal like this. Yeah. Then with arrow key I can move and bring it here. Fine. So I have made all the contacts for the inputs, and now I can actually bring this MOSFET closer and join with it. So I will select this whole thing and I can actually drag it with arrow key. So I brought it here. Now left click, right click, joins this polysilicon. Left click, right click here, joins this polysilicon. Let me check if I have not made any error. Fine. Again, left click, right click, joins this polysilicon. Left click, right click, joins this polysilicon. So I have made all the contacts and no errors. That's good. So what do I do? Need to do now? I need to make the connection for the output node. So from the stick diagram, you can see that this is the output node, that is drain of transistor B and transistor D, and the drain of transistor D. They are connected together. So I will left click here, I will bring my metal here, and I will right click here. So this way it got connected. I can make a little. Let me see if it is fine. So it is showing some error. So what error is that? Okay. So there is an error that this metal line is closer to this metal. So how can I address that? I can bring it a little away from that metal. Again, it is showing error. So that same error, you see that the separation between the two is not sufficient. So okay, on. Now there is no error. So this becomes actually iterative process. Initially, you will have to you may have to do many iterations, but with practice, we will be able to cause less and less design errors. So now it is time to create export pins. So I shall have in here for the output, and that actually is connected. So now it is time to create the ports. So this layout is actually free of design rule checks. So it has passed the design rule check. It is free of any error. Now let us create export ports. So I will select this and I will go to export, create export, and I will select VDD, and this is power. So I will do power. Okay, so VDD got placed there. Similarly, I will select this and I will go to export, create export, and then this is GND, and this is ground. So that ground got placed there. So now I can actually turn it white so that text may be visible more clearly. So if I go and select white background, okay, so that's it. Okay. So now I will select this, and this input is, if we see the schematic, so the first transistor is transistor A. So I will go here first and I will see the schematic actually. So you have VA, the name for this input is VA. So we will also name this code export code, create export, and we will name it as VA. And this is an input, so I will write input. So similarly, we have what is the next VP? So we will name this input as VP. So export and VB. Fine. Then after VB, I think it is D. So VD. No. A B. Let me also see this. Oh, sorry. We shall not refer to this. Rather, we shall refer to uh, the stick diagram actually. The first transistor, that is C transistor. So that shall be VC actually. So this export shall be deleted. This export shall also be deleted, and we shall again create export. Let me see that. Okay, we shall again create. This is export, create export, and this is actually VC input. Then after C we have transistor A. So this is VA. Create export VA. Then we have B. So this is VB actually. Create export VB, and then we have B. Create export VB. So we have created export, and then we need to create output. So the name, what is the name of the output? Be out. So name shall remain same. So we will select this pin, go to export, create export, be out, and this is an output. So out. Fine. So far, it's okay. So we have actually created the schematic view of that circuit, and now we have also created the layout view of the circuit. And after doing the layout and running the DRC, we have made sure that this layout is clean of any design rule violations. So there are no design rule violations in this layout. Now the next thing that we shall ensure that this layout actually is in agreement with the schematic. For example, in the schematic, we can clearly see the connections, and we can ensure that the connections are as per our requirement. So it is easier. Verify the connections between different terminals, between different components is relatively easier in the schematic view of the circuit. However, it is a little difficult to verify the connections between different terminals, whether those connections are as per our requirement or not. So that is little difficult, by means visual verification of those interconnects are actually difficult, and this is a simple layout consisting only 4P MOSFET and 4N MOSFET. Therefore, we may be able with little effort to even visually ensure the terminal connections, but you can think of circuits having hundreds of transistors and the connections thereof. So there it will really be near to impossible to verify the connections visually. Therefore, the layout tools, they actually offer us a tool that verifies the connections between these components with the connection of the schematic, means it ensures that the connections between different components, different terminals is same as the connections in the schematic. And for that, we have a tool that is generally referred to as LVS, layout versus schematic. So our layout shall pass the LVS, layout versus schematic. So if our layout passes that test, layout versus schematic test, it means that our layout is correct from the connection point of view also. So that same LVS tool is known as NCC in electric. So in electric, that LVS tool is known as NCC. NCC stands for Network Consistency Check. Whether the connections in the layout and connections in the schematic are consistent or not. So that LVS tool is known as NCC in the electric VLSI design system. So let us run this NCC and see whether this layout passes that LVS or not. So I will click on this, and the report of LVS is populated here. So let me see what it says. That export match means the input and output nodes that we have created, that matches. Then another thing, shall I maximize it so that you can see it? Okay, let me maximize it, magnify it rather. Let me magnify it. So when I magnify it, so you can see the report of the LVS here. So you can see comparing this schematic view with the layout view. I have named the cell as an example. So you have the schematic view of the example, and you have the schematic layout view of the example. So this NCC is comparing. Now the it is report is exports match. Exports match means the ports that we have created, the name of those ports, they are matching, and that is actually the requirement. Then topologies match. Topologies means the connection between the terminals of the components, the transistors. So topology is also matching, and the sizes of the transistors are also matched. So these are the three important requirements, that the exports shall match, the topology of the circuit shall match, and the size of the transistors in a schematic and the size of the transistors in layout shall match. So we have actually passed this network consistency check. Now, once we have passed the network consistency check, we can simulate and see the behavior. So for simulation, what I can do, I have already created this SPICE command. So I will simply select it, and I can go to edit and copy it, or I can use Control C also. So copy, and I will go to layout view of the cell, and I can actually paste it here. So I have pasted that. Okay. So here the text sizes are little small, so I can go to text and increase all text sizes. So that can be done by shortcut key also, by pressing Control and equal to sign. So I will press Control and equal to sign so that the text sizes are increased. So you can see all those commands here. This I don't know why it happens so, this visibility. So it may be system dependent, but when you double click on, you can see that these commands here. Okay. Now let us first simulate the schematic view, and then we will simulate the layout view. So in the schematic, what actually I have done, so it is the cells are actually related. So this is this is something system related issue. So I have done what? I have set the inputs such that only the D input is changing. I am only changing the D input, and rest of the inputs. Okay, let me first edit it. This happens. So we will have to bear with these sort of issues while using the free tool. So I have done what in this? I have fixed the A, B, and C inputs at supply, and I am changing. I have applied a pulse input at D. So you have this transistor D and this transistor D. So this actually gives you inverting behavior on it. So I will go to tool and I will simulate. So write a spice there, and then I can see the behavior. So I have B, D here, and I have B out here, and here it is. So we shall get similar output from the, and I have also added some measurement uh, commands to measure the delay. So that's it. So let us go first and see the simulation of this thing. So let me go to tool and run the spice deck, write spice deck. So now here we are having some error. So what is that error? MP-MOS3 cannot find definition of model SPICE model. So I think I forgot to specify model for some MOSFET. Let me go to the layout view. Okay, yes, I can see that. I can see that I have forgotten to edit this SPICE model for this MOSFET. That one. I forgot to edit this. So this shall be PMOS. Fine. Save. Now again I go to Spice and write Spice deck. Now it has run, and you can see the BD. I can see there is BD. Okay, if we are seeing actually many inputs. So what we can do actually, there are pins. There are pins, so many pins created while doing the layout. So before we run, we can go to edit and we can actually clean up cell and clean up pins. We can do so. 5 pins have been removed. They were the redundant pins that were there. Okay. So now let us again go and okay. Let me first exit from here and tool spice, write a spice deck. So now I can try plotting this V out. Let me locate it out. V out and VD. So I can see VD. Yes, I can see VD and V out here. So okay. So I'm getting that behavior. Fine. I'm getting that behavior. However, I would like to like your attention that you compare the netlist that has been extracted after doing the layout. So the netlist that have been extracted after doing the layout. So this is earlier you were having only length and width of the transistor. Now it has put the source area, drain area, perimeter of the source and perimeter of the drain for all those transistors. Apart from that, all the parasitic capacitances and resistances that are there, so all that has been extracted from the layout, and we can actually compare the delay of this post layout simulation with pre-layout simulation, because the delay of post layout simulation will be larger because of these parasitics. So parasitic extraction step has been performed, and you can see all the parasitics have been extracted for this layout. So let us go and see the delay measured for this post layout simulation, and later we will compare it with the pre-layout simulation. So here we can see the delay. So this delay is 42 picoseconds. So okay, let me write this value. The delay you can see is 42 picoseconds for post layout simulation. It is 42 picoseconds. You can see the delay that we got from post layout simulation. It is 42 picoseconds. So I will exit from this simulation and I will go to a schematic view and I will again run the simulation, and you are here, so we can again go and check the delay reported by pre-layout simulation. So you can see that pre-layout simulation reports delay of 20 picoseconds. So 20 picoseconds is the pre-layout simulation delay and 42 picosecond is the post-layout simulation delay. So you can now appreciate that while going through various design steps. So you start with the schematic entry of the design and then you do the pre-layout simulation. So even when your pre-layout design matches the design the delay constraint, what could go wrong after doing the layout, your timing check will fail. You may not meet the timing requirement of the circuit. And that is why this custom design is actually iterative process. You will have to go back and correct resize the transistors and do the corrections for meeting the delay requirement. So I think this is what I wanted to do today. So one thing that you may have noticed that those who have used Cadence, that doing layout in electric is not as simple as in Cadence. Cadence offers you many advantages that you have a schematic drawn layout where the transistor along with the appropriate sizes are placed from the schematic to the layout view. But that is actually a trade-off. So either you shell out 15 lakh rupees for buying Cadence licenses, and if there is some constraint on the finance point of view, still you can go ahead and teach your students the layout. So that your students are not deprived of a hands-on experience of doing the physical design and the experience on physical design layout of circuits that will actually add value to the resume of your students, and they will actually feel it easier to get into the VLSI industry. So thank you very much for your attention. So this is what I wanted to discuss today. Now the session is open for questions and queries.
Questions, please.
So Vismita is asking that is it a cadence tool? No, it is not a cadence tool. It's a free tool named Electric VLSI Design System. So you can use it for free and you can train your students on IC design. So your students can have hands-on experience on IC design. It's a free tool, but the flow and the experience is similar to cadence.
Is there any other question?
So I had a few questions.
Yes, please.
Yes, sir. So in this electric, there's an option for checking the body connections as well in layout versus while performing layout versus schematic. So actually, I'm trying to simulate an inverter, and I was facing some issues with that. So could you please address that? So
Actually, I can address your issue, but verbally the error that you are getting may not be clearly conveyed. So I can address that issue only when I see the layout and then I see what error is reported. Then of course I can try and address the problem.
okay.
If you are ready with your screen, you can share your screen and I can see and try to uh, answer you.
Okay, so I can do that right now.
So I am stopping. I am stopping sharing, and you can share and the screen, and then I can see what is going wrong.
Okay. So I'm not able to.
8 minutes. Are you ready with your screen layout?
Yes, I've created a layout for an inverter.
Wait. Yes, I'll have to do that. Even.
Yes. Um, uh, is my screen visible?
So what is the error that you are getting?
Yes, sir. So in the preferences, if we check this transistor body connections,
Yes.
then while performing a layout versus schematic analysis, I get this error. Just do that.
So, okay, so can you open your schematic?
Yes.
I saw it. Can you open your schematic?
Yeah, it's open. Is it visible?
No, I am seeing the layout. Please open the schematic viewer.
Schematic. Okay. Okay. Yeah. This is the schematic.
Okay. Yeah. So you have created a four-terminal device here also. That's
Yes.
fine. That's fine.
So if I do this layout versus schematic now
Okay.
under NCC,
Yes.
then I get these errors which
So you
say
have
that
actually many wire-related errors also.
yes, sir. But if I uncheck that in under preferences, then I don't get any errors. Uh, so just wanted to understand what error
Okay,
exactly
this will
is.
actually be difficult for me to pinpoint the error. So what I would suggest you, when you could be going wrong, because many times what happens that you can see that different layers or different regions, they are overlapping with each other. So you will have to ensure the connection also. So there is NMOS with body N4 in cell tutorial, uh, wires attached, three wires attached, four wires attached. So okay, you close this window.
So
So it is showing some error here. Now it's near well to body contact. I'm
yes,
feeling it, I'm feeling it a little difficult to just diagnose the error. Is what could have gone wrong. What I can suggest you that you shall try doing it again. Initially, it happens so that we make some error and then it becomes very difficult to identify that error. And remotely identifying that error remotely, that becomes very
okay, all right.
I could not pinpoint and tell you this.
Vinay,
Yes,
that
sir.
that background material I can see two times. What editing you did?
So which
Body kind of material. Na? Yeah, I can see there are two layers, different layers. Background, if you see carefully. I don't know whether it is
okay.
illustrated or not. I
No,
think
sir. Actually, this is the PMOS over here on top, and below we have a connect. Below I've connected NMOS.
no, but their layer.
So
I think that sizing there is an issue. ठीक है, okay, we will see later.
okay, no problem, sir.
Yeah. I'll have to see it and again or else again start, but then don't uh, just stretch layers like that. I can see here there's some space left right side. You might have tried to edit the layers. Okay, it's okay. We will see it later.
Okay.
Anything else?
Yes, I had a couple of more questions.
Okay,
Uh,
go ahead.
yes. So what I understand, sir, is that layout versus schematic is essentially a tool which can be used to validate the layout against a schematic. So I just wanted to ask, sir, is there any other tool which can be used to validate a layout against a netlist code rather than validating it against a schematic?
I'm not aware. Actually, LVS itself means layout versus schematic. That is, you are validating your layout and the interconnections thereof with the schematic. So that same LVS is known as NCC in electric. But what you are saying that layout, validating layout with the net list is that
Yes.
textual design entry you mean?
Yes, sir.
No,
Essentially a spice code.
why do we need to validate a layout with textual design entry? See, for a design entry, that textual design entry is not a good approach. That is okay when you have only few transistors. The standard design entry is done using a schematic only. So it's always the schematic based design entry. You see the flow, design flow, custom design flow. So you will have that schematic design entry, then pre-layout simulation, then layout, and then post-layout simulation. So for a smaller circuit, it's okay. You can do the schematic-based design entry, that textual design entry. But then also in textual design entry, you have chances of making wrong connections, and that can be easily avoided when you do schematic-based design entry.
Okay, sir. And one more question, sir.
Yes, please.
Currently, like I have just simulated a layout for an inverter, which typically has smaller aspect ratios. But if we want to use transistors with larger aspect ratio, typically for analog
Yes.
based,
Then, yeah, actually, I do not have time for that. You will have to use multi-finger transistors. You will have to break the transistors. So you will have to use multi-finger transistors in that situation.
okay, so electric supports that, right? Multi-finger simulation.
Pardon?
Electric does support that multi-finger layout
Yes.
simulation.
Multi-finger transistor is nothing but you will be connecting transistors in parallel. So that supports it. No issue.
Okay. Yeah, that's it, sir. Thank you so much.
Now there are a few queries in the chat box. So let me go through it. So there is one query, sir, these results are suitable only for academic learning purpose or beyond that also. So personally, I have used these free tools for doing the layout and I have published paper. So I never faced any criticism for doing the layout using free tools for because I use those layout for comparing the area. So that I have not faced any criticism for that because it is accepted, it is known that those industry standard PDK that are not that easily available everywhere. Then second query is one can compare layout with netlist using caliber, a mentor graphic tools. Okay, I am aware of that caliber, but I don't know what is the query actually. What do you want to say?
No, sir. No, sir. That is. I think that is not query. Sir is
This is like a statement.
he is telling the statement that it is possible.
Okay,
Yes.
Saima Bashir is there now. This is a statement, I think. So,
Yes, he is telling.
of course, it is good if the mentor graphics and that mentor graphic tool is available to you. You are fortunate, of course. You can go ahead and use those tools. But my focus was to familiarize or just bring it to the knowledge of a wider cross section that there are free available tools that can be used to train your students for doing layout. So even if right now you do not have licensed or commercial tools, if your students are familiar with the layout using these free tools, they can easily and in a lesser time migrate to commercial tools and they can do good.
Yes. Correct.
Okay, Saima.
Okay. Anyone else? Speak.
Okay,
Last.
there is one
Submit.
important query. There is one important query. If we are designing analog circuit using technology that as TSMC 180, will the design rule remain the same or are they different? Actually, this electric follows lambda based design rule. So what you need to do, you shall go to preferences and go to tools and technology and you shall go to scale. So if you are using 180 nanometer, so I have set the lambda as 100 nanometer. Similarly, if you want to do the layout and simulation, say for 65 nanometer, so you can set the lambda 30 or 40. So it's following a lambda based design rule. You can set the scale half of the channel length to be approximate, not very accurate. So you can put a lambda here, adjust lambda here. And that is what you can do actually. So it's a free tool. You don't have any PDK with this tool. So you can just adjust the lambda and go ahead. So any other query?
Naushad sir, if he's having PDK from TSMC available, he will be able to integrate here, no?
Pardon, sir?
If he is having the PDK from TSMC available.
No, TSMC PDK, how you can integrate,
That
that
won't be possible.
actually is a complex issue. You will have to go into the preferences and then you will have to individually edit the design rules and other things.
Okay. Yes. One more question.
Okay, another question is, we simulate device like MOSFET, CNT in electric. See, for what kind of devices you can simulate actually depends on the LT-SPICE, because the simulation engine is SPICE engine is LT-SPICE. So LT-SPICE I think don't support this CNT because CNT is Verilog based model. So Verilog based model is not supported by LT-SPICE to the best of my knowledge, but LT-SPICE supports BSIM4 model. So you can simulate 45 nanometer CMOS, 32 nanometer CMOS, that you can do. I have done. BSIM4 model is supported, but Verilog based CNT model, etc., I'm not sure whether LT-SPICE supports that. So that will be actually over expectation from a free tool available.
इंद्रजीत सर, फ्री में इतना ही हो सकता है. So basically good for MOSFET CMOS design.
Yes, sir. Yes, sir.
Because MESFET, MOSFET, CNT, even if you see the device simulation, that is also very complex. It's not available freely. Anything else? Good. Anyone else? If you have, you can ask. Because as such, this is the last session of our technical aspect, first STTP technical session, I would say. No more questions? Okay. Sneha madam, are you there?
So Rathore sir,
Yes, sir.
हाँ मैडम, हाँ सर, हाँ सर, बोलिए सर.
नहीं वो मैम कुछ क्वेरी है क्या मैम?
नहीं, मैं वो आपका
एक
सर्टिफिकेट.
पॉइंट मैं थोड़ा सा हाईलाइट करना चाहता हूँ.
हाँ बोलिए.
So will you allow me to share the screen?
हाँ ओके, नो प्रॉब्लम, नो प्रॉब्लम. Go ahead. I'll give it back to you. Just a minute. No, these are important issues because no one use the training or demonstration on
Yeah,
this kind
thank
of
you.
setup.
I would like to point out one important thing that let me first. Yeah. So what you can see here, now you can see the benefit of putting the contacts like this. Otherwise, initially I could have put these contacts all over the active region and these contacts all over the active region. Is my screen visible, sir?
Yes, clear.
So now you can see that had I put these contacts all over the active region, I would not have been able to run this metal line like this. So this will consume actually area and increase the vertical height of the cell. So that comes with experience. You will have to guess and you will have to take right decision where to place the contact and how many contacts you shall place. So whenever the space is available, actually here I should have put all the contacts because adding all the contacts will reduce the contact resistance and that is good for circuit performance. So here I could have put all the contacts, here I could have put all the contacts, but here I cannot put all the contacts. If I put all the contacts all over the active region, so I will have to run this metal line here and then all the other things will shift down and that will actually increase the area of the cell. So when we are trying to minimize the area of the cell, we shall plan things accordingly. That is what I wanted to point out. Thank you, sir.
Okay, sir. In our next this thing, STTP, I think on let me see the day. I can tell you the date also. I think 4th November or something like that. We have a session on the analog layouts from that cadence. 1 day session again the layouts, but it's an analog layout. So no more questions. I'll take to Sneha madam. Sneha madam.
Yes, sir.
I think there are no more questions. Thank you, all the participants. It was nice interacting with you.
No, sir.
Sir, thank you, Naushad sir. Thank
Thank
you
you.
for and a big thank you for adjusting our schedule. You are the first resource person who got affected on Monday because of our power cut, and you immediately within 5 minutes you agreed to rearrange the session, reschedule the session, and that's not an easy task. So thank you very much. Thanks a lot, and for taking three sessions and showing the demonstrations. And all participants, I'm sure they have enjoyed your sessions. And it's not an easy task to show demonstration in an online mode. Right? So thanks a lot. Thank you very much, and we'll be looking forward for in analog also. You have the session there also, right? So we'll be looking forward in those sessions also. Thanks a lot, Naushad sir.
Thank you, sir.
This is your
Thank
set.
you all.
Okay. Thank you very much. So participants, tomorrow we have examination, right? 10 o'clock, Moodle platform, please, 10 to 11. 1 hour examination, 60 marks, objective type questions, and afternoon we will have a validatory session. We will start at 2 o'clock, validatory session, and we have the first kind of a motivational speech. He is a very popular, renowned speaker, Dr. E.V. Swaminathan, and he is a mentor for many industries. So please attend his session. It will be very valuable. Stress management kind of thing, so that you are relaxed at the end of one STTP. So that's why we have invited him, and he agreed to talk about stress management. So please join first for the test on Moodle platform, and then for the validatory session at 2 p.m. Okay. So thank you very much. Thanks a
Sir,
lot.
how many questions are there? Hello?
Madam, I'll set now.
Sir, 60 marks, 60 minutes and 60.
Don't worry, don't worry.
Naushad, sir.
Yes, I'm here.
Sir,